All right, hello everyone. Welcome to my exam 3 review. Today we'll be going over alkyl halides and elimination reactions, alcohol, ethers, epoxides, thiols, and sulfides, and alkenes. And I'll be going through it in that order. Each chapter will probably take 45 minutes to an hour. And I do have a few practice questions for both chapter 8 and chapter 9, but not chapter 10, because I want to take a little bit more time to talk about chapter 10 as a whole when we get there. Okay? So, first we are going to be talking about alkyl halides and elimination reactions. So, I personally think that elimination reactions are a little bit easier than substitution reactions because of a few reasons. So let's look a little bit more. We can see that when comparing substitution and elimination, substitution looks to be a little bit simpler because we're using a nucleophile and only replacing what's on this carbon that's attached to the alkyl halide. However, it's important to note that most bases will also be nucleophiles. And when we're talking about bases, we'll be talking about the Bronsted-Lowry definition, where they are proton/hydrogen acceptors. So a nucleophile, so like in this case, our nucleophile would be OH negative. We can see this is a base, and it's also going to be a nucleophile. There are certain structures that are bases but are not nucleophiles, which we will talk about in a little bit. I'm just going to delve a little bit deeper into elimination. So when we talk about elimination in this class, we'll be talking about something called alpha-beta elimination. And what this means is we will be eliminating a leaving group from the alpha carbon, and then we will be eliminating a hydrogen from the beta carbon, and then we'll be making a new double bond between that alpha and that beta carbon. And the reason why we have to get rid of this hydrogen and the leaving group is because if you recall, carbon can only have 4 bonds. So let's take this example real quick with the Br, and I'm going to draw it out with its Lewis structure. So we can see that the C is attached to one Br here. And remember, when we're drawing line angle structures, there are quote unquote invisible hydrogens that we don't see that fill up a carbon's octet. So we can see here, here's the alpha carbon, here's the beta carbon. And we can see here that if we get rid of the Br, now that carbon has 3 bonds. It wants 4 bonds, but it can't make a double bond with our beta carbon until that beta carbon gets rid of one of its hydrogens. So that's why we have to use the base to go ahead and grab on to that hydrogen there, and then the bond that was making that hydrogen that was making that carbon hydrogen bond will move to become a double bond right here. And this is because when the leaving group leaves, it takes all of the electrons with it. So we have to get the electrons for the double bond somewhere else, and that somewhere else is that beta carbon hydrogen bond. Okay, and we'll get into this a little bit more. Now, I talked a little bit about how some bases are not nucleophiles. Generally, the rule is that if you are a base, you're usually also going to be a nucleophile. However, when there's a lot of steric hindrance, and recall, steric hindrance is when a molecule has a lot of junk in the trunk, so it has a lot of substituents on it. Like this, for example, is tert butoxy. Sometimes you'll see it written out like this. Oop, let me make that Y a little better. Okay. And tert butoxy, you can see here that it has all of these methyl groups right here behind it. This causes this to be really bulky and have a really hard time replacing things. Like, let's take this example right here from before with the Br. It's going to have a really hard time replacing that Br because of all of this stuff in the back that is causing that steric hindrance. And you can think of this as sort of like something with a lot of steric hindrance can be like a big truck with a lot of stuff, basically. And you can think of nucleophiles as generally being really small, like bug cars. And you can think of this carbon right here that has the leaving group as a parking space. The little car aka a small nucleophile, is going to have a lot of an easier time replacing and getting into that parking space than a big truck like tert-butoxy. And I'll use this truck bug metaphor a little bit more later. I just want to explain why some things are a base but not a nucleophile. So strong bulky bases, like I'm going to use the same example again, like tert-butoxy, are strong bases but are weak nucleophiles. Okay? And we can see nucleophilicity weakening as steric hindrance increases. So if we have something like OH versus OH negative versus a methoxy, so that's just a CH3 attached to an O negative, we can tell here that OH is going to be the better nucleophile because it has less steric hindrance due to hydrogen being much smaller than a CH3 group. And so that trend will occur, that trend will follow as we add more substituents. Okay, so when we're talking about alkyl halides in elimination, we'll be talking about something called dehydrohalogenation, and all that we need to know about this reaction is in the name. D means we're losing something. Hydro means hydrogen. Halogen means we're losing a halogen. So we're losing a hydrogen and a halogen, and the halogen is going to be our leaving group, so right here, and then we're losing a hydrogen due to our base, so it's dehydrohalogenation. And we'll see a lot more of this name stuff, like the organic chemistry reactions having names that directly relate to what is happening, and we'll see that a lot more in chapter 10. Okay? So let's continue on, and let's talk about how whenever we have one alpha carbon and multiple beta carbons, we're going to get two different possible products. And the way that we determine which one of those possible products is the major product and the minor product, which means the major product is the one that's more likely to form and the minor product is the one that's less likely to form, is to look at the alkene stability of the products. So recall, when we're talking about alkenes, there are a few stability rules that we have to keep in mind. The more R groups, which essentially means the more carbon-based groups that a double bond has attached to it, the more stable it is. So if you're monosubstituted, you have one R group. You're less stable than a disubstituted with two R groups, less stable than a tri, and less stable than a tetra. So if I were to compare, like let's say that I wanted to compare this this alcohol, or no, I'm sorry, not this alkyl halide, but this alkene versus this alkene, we can see here that this alkene on the left is going to be monosubstituted, and this alkene on the right is going to be disubstituted. It's important to note that even though we are talking about R groups, there are still invisible hydrogens here that we just don't draw. Don't forget that those exist. We do not draw them and they don't count as R groups, but it's important to recognize they are still there. Okay, so we can see that this one is going to be more stable than the monosubstituted one, and so on. So now let's talk about something called cis and trans. So when we talk about cis and trans in relation to a double bond, we will be talking about the relation of two groups that are the same. And what I mean by that is we can see here that in both of these examples, the hydrogens are highlighted in blue and now in pink that I'm highlighting them. And we can see here that when it's cis, the two hydrogens are on the same side, and when it's trans, the two hydrogens are on opposite sides. Cis and trans can only be used when there are two of the same group, one on either side of the double bond, and in this case, this would be the hydrogens. There is another system of naming and classification that we get into more when we're talking about alkenes that is a little bit more broad in its definition and will include something that does not have two of the same group. So, for example, if instead of having an H here, this guy had an OH here, we couldn't use cis or trans because we don't have two of the same group that we're comparing. So instead, we would have to use that other system that I will explore a little bit later when we enter chapter 10. Okay? And so then those are the general stability rules for alkenes. And so when we're talking about elimination, and we're talking about elimination that creates two possible products. So if we look here, we say, oh, here's our alpha carbon, and generally the alpha carbon is going to be the carbon that's attached to leaving group, or if we're talking about a carbocation intermediate, the carbon that contains the positive charge. But in this case, we're just going to make the carbon that's attached to the Br our alpha carbon. And then the two carbons next to it are going to be our beta 1 carbon and then our beta 2 carbon. So if we take a hydrogen from beta 1 and we make that our double bond, we end up with this guy right here. And then if we take beta 2 and we take its hydrogen from its carbon, then we end up with this. We can see that beta 1 is 1, 2, it's di-substituted, and beta 1, 1 is mono-substituted. So the beta 1 product is going to be more stable, and thus, if we are using a small base, which is most bases like OH, then B1 will be our major product, okay? And then that means that the beta 1 will be our beta 2, sorry, this should be beta 2, will be our minor product. And we also call this more stable product the Zeitstev product. And we call the less stable product the Hoffman product. Okay? And so a lot of the time, the Zeitstev product will be your major product. However, in some special cases, the Hoffman product will be our major product. And that Hoffman product will become our major product when we are using a big bulky base. And this again is because of its steric interference, or steric hindrance, not interference. So we see here, again, we can imagine this guy here, this terp butoxy, as a big truck. And we can imagine each of these betas as parking spaces. Beta 1 is a small parking space, but it's sort of preferred. It's near to the door that you want to get into. And beta 2 is a big parking space, but it's sort of farther away. So if we have a small base, like OH, which again is going to be our tiny little bug car, it's going to be able to fit into that small space easily and create the beta 1 product. However, if we have this big truck right here, it's not going to be able to fit in that small space. Rather, it's going to be forced to go into that big parking space and make B2 our major product and make the Hoffman product the major product. Okay? So just to reiterate, when we have two possible products, the more stable product is going to be known as our Zeitstev product, and the less stable product will be known as our Hoffman product. The Zeitstev product will be our major product when we're using a small base. The Hoffman product will be our major product when we're using a big, bulky base. All right? And I think that's what these slides that are coming up sort of explain. Okay, so here we are going to be talking about the mechanism of this elimination reaction, and it's very similar to the mechanism of the SN1 and SN2 reactions, if you're familiar with that. So what happens, at least in E2, so recall E2 is going to be our one-step reaction, and E1 is going to be our two-step reaction. Okay? So we can see here in E2, everything happens at once. The leaving group leaves, the base grabs onto the beta hydrogen, and then the beta carbon hydrogen bond becomes our new double bond. However, in the E1, the leaving group leaves first. We have our carbocation, and then the base grabs onto the hydrogen, and then that carbon hydrogen bond becomes a new double bond. So we can see here that E2, everything happens at once. E1, we make a carbocation first, okay? And so, let's scroll down a little bit. So when we're talking about E2, again, similar to SN2, it's all one step. So our reactants, our substrate, which is the alkyl halide in this case, and the base are going to factor into our rate equation, make our rate equation second order, and then that's where the 2 comes in with the E2 name. On the other hand, I'm going to scroll down a little bit. I think it kind of moves on. Right here. So E1, we have 2 steps. And remember, when we have 2 or multiple steps for that matter for a reaction, a chemical reaction, we have to consider only the reactants of the slow step. So in this case, we are only going to sort of consider the substrate, aka the alkyl halide in this case. So this reaction is first order, and thus it's going to be known as E1. Okay? So let me scroll back really quickly and let's talk a little bit about E2 again. So E2, let's continue on. Let's go back. So E2 prefers a tertiary carbon. And if you recall, tertiary carbons are generally very sterically hindered, so you might be wondering to yourself, well, SN2 doesn't like tertiary, so why does E2 like it? Well, E2 likes it because it's not trying to get into this space. It's not trying to replace anything, so it likes a tertiary carbon or tertiary alkyl halide because if we look at its transition state, we can see that the transition state has a partial double bond. And the more stable that partial double bond, the more stable the transition state and the lower the activation energy. So if we have a more substituted alkyl halide, that's going to be better for E2, and it's also going to be better for E1. Because, let me scroll down really quickly. If you recall, E1 makes a carbocation. And if you recall from before when we're talking about SN1 and SN2, a more stable carbocation is a more substituted carbocation. So if E1 is going to occur faster, it's going to want to create that more stable carbocation. It's going to want a tertiary alkyl halide. So both E1 and E2 prefer tertiary alkyl halides over secondary over primary. Okay? And elimination reactions don't occur with methyl groups because they don't actually contain a beta carbon to make a double bond. So let's skip back to E2. So the way that E2 works is that it's going to, again, try and make the most stable product possible. But what's also important about it is that it's going to eliminate things anti-periplanar. And what this means is you're basically going to eliminate things that are opposite to each other. So we can see here that this hydrogen is up, this X is up, so they're syn periplanar. They're on the same side. Anti-periplanar, hydrogen is up, the leaving group is down. They're on opposite sides, so they're anti-periplanar. And this comes into play especially when we're talking about something called cyclohexanes and the chair conformation. I know how everyone always loves the chair conformation so much, so I bet you're all very glad that we're coming back to this. But essentially, when we're talking about the chair conformation, when we want to eliminate something, the leaving group has to be in the axial position. Because if it's in the equatorial position, it's just really stable and it's not going to be anti-periplanar to any hydrogens sufficiently. Okay? So if we look here, when we have the chlorine axial, it's going to be more available to attack to leaving overall. But we also have to think about the hydrogens that are going to be eliminated as well. Because remember, when we talk about elimination, we have an alpha carbon, and then we have the beta carbons connected to it. And those beta carbons have the hydrogens that are going to be eliminated. So I'm going to draw those in really quickly. If you need a refresher on the chair conformation, I would go back and watch my other office hours if you can about this stuff. But I'm just going to move on from it now just because I want to get through all of the content today. And so when we're talking about anti-periplanar, we're going to be talking about something that's opposite to the Cl. So it has to be up and axial. So here's an H that's up and axial. Here's an H that's up and axial. So both of these beta carbons could have a double bond theoretically. However, let's say instead of having a hydrogen right here, this guy has something like an OH. Now we have an OH anti-periplanar to the Cl, and we can't exactly eliminate an OH like we can a hydrogen with a base, so we cannot make a double bond right here with this beta carbon. And this comes into a lot of different examples, like every single test, every single chapter 3 test has a question about anti-periplanar stuff. Not chapter 3, I'm sorry, exam 3 has a question about anti-periplanar stuff, and I personally, I got that wrong on my test, but I never forgot. So I always make sure to sort of hammer that in. Okay, so we talked about E1 reactions. The substrate, again, E1 prefers tertiary. Let's continue on. Okay, so let's talk about something called shifting. Whenever we have a carbocation, we can have a rearrangement that will make that carbocation more stable. So let's take this example real quickly. And one thing to note is that whenever we see heat in our reaction, let me get a different color actually. Whenever we see heat in our reaction, that's going to encourage the elimination reaction to occur. Because remember, when we're breaking bonds, we want to put in energy, and when we're making bonds, we give off energy. So if we put in enough energy, then we're going to break more bonds than we make. Okay?
Question, Casey,
Go ahead.
does it mean that it prefers elimination or like E1 in this case?
In this case, it will be E1, but overall, if you have heat, it's going to prefer elimination.
Got it, thank you.
And also, one thing I want to talk about is E1 as well as SN1 prefer weaker bases and weaker nucleophiles. And this is because it wants to have that chance to form a carbocation before the base or nucleophile attacks. And because of this, I'm just gonna go back for a second. We'll come back to this in 1 second. And because of this, because we form I'm gonna scroll back up to that mechanism that we saw here. Because we form a carbocation and we're using the same type of nucleophile / base, SN1 and E1 will always occur simultaneously. So while it is not drawn here, oops, that's not what I meant to do, but while it is not drawn here, the SN1 products will also be present in this reaction. So if we think about it, this guy is going to have 1 and then 2, 3 products. This guy overall, this reaction will have 3 products because remember when we do SN1, we are going to have both a inversion and and then it will keep the same stereochemistry from before. So SN1 will make 2 products. The elimination only makes 1 because if we see here, all of these beta carbons are basically identical and will make the same product. It'll all make a double bond attached to a propyl group. Okay? And I'm sure you guys are about to ask about that, but I hope I answered that question. So let's continue on really quickly. So back to this. So like I said before, SN1 and E1 will always occur simultaneously, but if there is heat in the equation, if there's heat being put in, it's going to favor the elimination. Okay? So the first step of E1 and SN1 is to do, let me actually zoom out a little bit, is to do the leaving group leaves, and we end up with a carbocation. So we end up with this guy right here. Actually, let me do black. This guy right here. And so we can see that we have a secondary carbocation. Whenever we have a secondary carbocation and it's next to either a tertiary or a quaternary carbon, it's going to do a shift. Similarly, if we have a primary carbocation, which we probably won't too often, but if it has a secondary, tertiary, or quaternary next to it, it will do a shift. We do not generally do shifts with tertiary carbocations because they're already as stable as possible. All right, so let's back to this. So we see here, we have a secondary carbocation right next to a quaternary carbon. So what happens here is, let me just remind you what a carbocation is. A carbocation is a carbon that contains 3 bonds and no lone pairs. And we know this because when we're talking about the formal charge, carbon has 4 valence electrons. If it only has 3 bonds and no lone pairs, it has a charge of +1, which matches the carbocation. So we can see here that here's our representation of our secondary carbocation. And it's going to be right next to a quaternary carbon. Okay, so what happens in this case is that quaternary carbon donates one of its methyl groups to the secondary carbocation. And we can see this in the line angle structure like this. And so then we end up giving this carbocation over here, we give it another bond in the form of a methyl bond. So now this guy's happy, he has 4 bonds. However, now this one that gave away the methyl group now has a positive charge. However, we can see here that the positive charge is now going to be on a tertiary carbon rather than a secondary carbon. So we have a more stable carbocation overall, okay? And so this shift would also occur if we had a hydrogen here instead of that CH3. So if it looked like this rather than what we had before. And what we did when we shifted the methyl group was something called a 1,2 methyl shift. And if we shift a hydrogen group, then it's something called a 1,2 hydride shift. And these shifts can occur whenever we have a carbocation. So it can occur with E1 or SN1. And so then we use our new, let me clear these drawings real quick and redraw it. So if we break this down one more time and draw the mechanism, oh, that shouldn't be a line here, that should be this. We can see here that the chlorine group, the leaving group leaves, the quaternary carbon donates one of its methyl groups, and we end up with this guy right here, the positive charge is here. Great. And this is why earlier I said that the alpha carbon is the carbon that contains the positive charge in the case of E1. Because now I'm going to name this one, oh, here's my alpha, here's beta 1, here's beta 2. Okay? If instead I had made this guy over here that's connected to the chlorine specifically, my alpha carbon, then we would end up with different products. Okay? So whenever we do E1, we have to draw the carbocation and find the alpha carbon from there. Okay? So now we end up with 2 possible places for a hydrogen to be grabbed by our H2O. Let me draw H2O real quick.
So Casey, we did the arrangement. Basically, when we do an arrangement, it's just placing the carbocation where we're going to have 3 substituents.
It's essentially placing that positive charge onto a carbon that would be more stable. So in this case, we made it tertiary. However, in other cases, we might make it secondary, but most of the time you're going to make it tertiary. I think 80 to 90% of the time you're going to make it tertiary. Okay? But be on the lookout for anything that could make it more stable. Okay? All right, so the next step of this reaction is our base either grabbing the hydrogen from beta 1 or it'll grab the hydrogen from beta 2. So if we look here, we can see the product when we grab beta 1 looks like this, And then if we grab the product from beta 2, it looks like, that is ugly. It looks like this. And you can see here, these two are basically the same thing, because we can see that if we sort of turn this guy around and see where the double bond lands, it'll end up being the same thing. Okay, and this is a little bit different from stereochemistry and stereogenic centers because there is no stereogenic center here. So we can't have we cannot have enantiomers at all. So these have to be the same thing. Okay, so we only end up with this single product here. And that's why it only has one product. Go ahead.
Sorry, is the alpha carbon the one that's the most stable though? How do you know like which one's
the alpha carbon is the one that ends up having the positive charge. So what happened here is we did the hydride shift and then our final carbocation looked like this. So then we put our alpha charge on our final carbocation.
Okay, I see. Thank you.
No problem. All right. So go ahead.
So the alpha carbon, like isn't that a methyl coming off the alpha carbon?
Oh yes, we could also have a beta. I was just demonstrating that yes, you're right. This would be a third beta. I was just demonstrating that we tend to get the same product sometimes. Okay. Just to recognize that these are the same thing, it would be the one product total.
Okay, so like if he asked for like all products, you'd have to draw that one also.
Yes, you would have to draw this. So if we made this beta 3 our beta carbon, then we would have a double bond right there, and this would be our Hoffman product in this case. and our minor product, because again, we're using a small nucleophile and base. But we can see here that while we do end up having 3 beta carbons, we end up only having 2 products. And I just wanted to illustrate that even if they look different, we're going to have the same beta carbons, or the same products with 2 beta carbons. Does that make sense?
Thank you.
No problem. Okay, so I'm just going to,
Really quick.
okay, go ahead. Sorry, let me undo.
And the alpha carbon is originally the one that has the leaving group attached to it, but then once.
Well, when we're talking about alpha carbons, when we're talking about E2, then yes, the carbon that is directly attached to the leaving group will be our alpha carbon, because everything happens in one step. We don't form a carbocation. But in this case, our alpha carbon is whatever carbon has the positive charge when the carbocation is final, like when it's in its most stable form. Okay? In addition, these shifts can only happen between adjacent carbons. So like notice how I didn't shift from this carbon over here. Like even if this carbon was a quaternary carbon, I would not be able to shift all the way from here to over here. So it has to be on adjacent carbons. It can't just be any carbon on the chain. Okay?
So then in E2, the alpha carbon is the one with the leaving group, but
Yes.
in E1 it's the one with the positive charge.
Yes, exactly.
Okay, thank you.
No problem. Are there any additional questions? All right, then I'll just move on. Okay, so when we're talking about E1 versus E2, I have a chart for this that I'm going to switch my screen to in a moment. I'll just switch my screen to it now. Hold on. So I have this here with, so somebody asked, so how will we know that we need to do a methyl shift? So I'm just gonna draw it right here, ignore my other drawings here. But whenever we have a secondary carbon right next to either a tertiary or a quaternary carbon, a secondary carbocation is next to a tertiary or quaternary carbon, then we can do a shift, because that will make the carbocation more stable overall. E2 reactions cannot undergo shifts because they don't form carbocation intermediates exactly. Okay? Does that answer your question about how do you know when we need to do a methyl shift? Okay, perfect. And also, you only really do methyl shifts when we have this quaternary carbon here. You're more likely to do a hydride shift when you have a tertiary carbon next to that secondary carbocation, because generally it's going to try and shift the hydrogen before it tries to shift a methyl group, because a hydrogen is sort of easier to move than a whole methyl group, okay? So I have these documents here that compare E1 and then, oops, that's not what I meant to do. That compare E1 and then E2 over here. This will be in the description of the video. I've also uploaded it to the chat in the live chat. And I also have this here, which compares the different types of reactions and how will we know which reaction will occur. Okay? What I like to do when I'm given a question that's like, oh, what kind of reaction is this and what kind of product we'll get? The first thing you have to do, or that I like to do personally, is I like to look at what kind of carbon, what kind of substrate that we have. If we have a methyl substrate, then that's easy because we're only ever going to do SN2. If we have a primary substrate, then we're either going to be SN2 or E2, because remember, SN1 and E1 don't really occur with primary alkyl halides because those are very unstable as sort of, what am I trying to say? They're very unstable as carbocations. Sorry. And then a secondary, we can do any of the reactions, and then tertiary, we only do either E2 or SN1 and E1. And notice again how SN1 and E1 are always going to occur at the same time. All right? So let's break this down. So methyl's easy, all SN2, so I'm just sort of going to skip that. Primary is a little bit different, because remember when we want to do a replacement reaction, we want to use a small nucleophile / base, so like negative OH. Whereas E2 elimination reactions, they're generally going to use these big bulky bases, at least when we're using a primary primary alkyl halide or primary substrate. And this is because, again, it's going to be a big truck trying to fit into a small parking space, all right? And then we usually don't see weak nucleophiles and bases reacting with primary alkyl halides. Okay, so now let's talk about, oops, I didn't mean to do that. Now, oops, hold on. Let us talk about secondary alkyl halides. So this one is probably the hardest one because you could do any of these overall. So a secondary alkyl halide will either be SN2 or E2 if we use a strong nucleophile and base, such as negative OH. Again, if we use a strong bulky base, then it's going to be E2. And then if we use a weak base, weak nucleophile, so like water, H2O, we're going to use SN1 rather, and E1, because again, it'll give it time to form that carbocation and then do a further reaction. All right. And then finally is our tertiary. Remember, both E2 and E1 and SN1 like tertiary, so all of these can occur. Whenever we have a strong base, a strong nucleophile, any one of the sorts, so like negative OH, the tert butoxy, it's going to be E2. Whenever we have a weak base in nucleophile, we're going to be doing H2O. Whenever we have a weak base, weak nucleophile like H2O, we're going to be doing SN1 and E1. And it's just one more thing to note is that whenever heat is added, it's going to prefer E1 or E2. And somebody said in the chat, I have a question about how would you know if it's a bulky base? Would it be the degree of the carbon? For example, would you consider ethanol bulky or small? So the major bulky base that you will see in this class is tert butoxy, what I've been drawing this whole time, this guy right here. It'll be very clear on test questions, at least I hope it would be clear, that it's going to be a bulky base. Like you're going to have tert butoxy, you're going to have like some sort of monster that looks like this. Ethanol would not be bulky. Generally, we consider bulky if it has sort of two groups coming off the same carbon that's attached to the oxygen. If it's sort of like a chain like this, we don't generally consider that bulky. We'll usually, because you've seen before, or in the next chapter, that we tend to use these long chains, these long oxy chains. That means just a carbon chain with an oxygen at the end of it. We generally use these for something called Williamson ether synthesis, okay? All right, so I think that answered your question. All right, perfect. And so now I'm going to clear this. Again, all of these documents will be in the description of the YouTube channel, or not the YouTube channel, but the description of the YouTube video as links to probably a Google Drive. All right. And so now I also have some practice questions prepared. Let me switch my screens to share my practice questions. So we can see here, I have questions 1 through 10 will be about elimination, and some of the questions will also be sort of considering SN2 and SN1 along with elimination. So questions 1 through 10 you should focus on right now. Again, this is going to be in the description if it's or if you're watching the YouTube video, this should be in the description. And then if you are in the chat right now, it should already be in the chat. And yes, that is basically all of chapter 8. Oh, there's one more thing that he sort of includes in chapter 8, and that is something called alkyne synthesis. And I'm going to use my Word document here to draw it. Alkyne synthesis is basically the creation of something with a triple bond. And if we remember, E2 and E1, elimination in general, creates a double bond. Okay, so if we already have a double bond there, then we can just do it again and create a triple bond. Oops, I drew that wrong. Okay, and the reason we draw it like this, again, is because the triple bond is linear, so we want to reflect that geometry in the line angle structure. And so to get to this point, we can either use something called a vicinal dihalide, which means the halogens are in the same vicinity, so they're on carbons next to each other, or a geminal dihalide, where both of the halogens are on the same carbon. They're sort of like twins. Okay, so all that is happening here is that we do E2 twice to make that this guy right here. So like E2 once to make this this alkyl halide with a double bond. Sorry, I thought there was like a special word for it, but I'm coming up blank. There probably is, and I'm not remembering it. So we do E2 once with these dihalides to make this special alkene plus alkyl halide. And then we do elimination again to create our triple bond here. So that's one thing to keep in mind for like questions in, I do know I have a question in these practice questions about that. You should be able to sort of pick out what is a dihalide. Can that dihalide or can this molecule form an alkyne through elimination, that sort of thing. All right. So again, if you're watching the YouTube video, pause at this point and try to do questions 1 through 10. And then when you come back, when you're done, when you try, we're going to walk through all 10 of these questions together. Okay? All right, so if you guys did that worksheet, we are going to go through every single one of these one by one all together as far as 1 through 10 goes, and then we'll do 11 through 20 when we finish up with chapter 9. Okay, so this first one, how many products are produced in this reaction, including stereoisomers? I'm going to be honest here, this one's really tricky, and the answer is going to be, it is going to be C here. I'm going to show you why in a second. So if we first look at this guy, okay, we have a secondary alkyl halide. Our carbon is secondary, and we have a weak nucleophile slash base. So that means that this is going to be SN1 slash E1. Okay, and of course we know SN1 is going to make 2 products because obviously SN1 is going to invert and then keep the stereochemistry of this one. So we'll get something that looks like this with OH here, and then something that looks like this with OH behind. But now let's talk about E1. So this one's going to be a little bit different. So we draw out the carbocation. There's no rearrangements because it's already secondary. It's as stable as it can be. And then now what we're going to do is we're going to we're going to circle the beta carbons in the drawing that I have here. So I have 1 beta carbon here and 1 beta carbon here. So it looks like we're only going to have 2 products. However, we also have to consider the cis or transness of these different different products. So let me move some stuff. So if I draw out, so this guy here, this guy has 2 hydrogens, or 3 hydrogens rather. So when we get rid of one of them, we're left with 2 hydrogens, and we're not going to be able to do any cis trans stereochemistry. Okay? And because we can only do cis trans stereochemistry if we have 2 different groups on either side, but one of them is the same. And so if we look over here, this guy's going to have H, this guy is going to have 1H, this guy's going to have 1H. And so if we get rid of one of them, then we can have cis trans isomers. So if I go ahead and draw that, we see we have this one here. And then, oops, sorry, my chat is freaking out. And then something like this. And would he ask something like this on the exam? Anything's free game. Like he could, I don't know. This was not one of the questions. Like, I don't know what he's gonna write on the exam, but he could ask something like this. Okay, so we can see here that we can have cis trans isomerism. So when we're talking about single bonds can move around freely. However, double bonds cannot. So when we're doing elimination, we could catch these 2 different stereoisomers. We could catch the single bond in either one of 2 positions, in a trans position or a cis position. And you can see here that both of these, they count as stereoisomers. So instead of having 2 products for E1, we have 3. So 2 plus 3 is 5, so our answer is C. Okay, this one is a very tricky one, and this one's a tricky one, but if you could do this on your own without any help from me, then it's amazing. So here's 1 product, here's 2 products, here's 3 products. This is the elimination product that I did not draw before. Here's 4 products, here's 5 products. All right, this one is definitely tricky. If you got it, then I'm really proud of you, but this question was designed to sort of trick you, which is why I made it, because I'm trying to make these questions a little bit harder than they might be on the exam if possible. Okay. So what is the rate of this reaction? So to do that, we have to look at this reaction. Well, we had to get, is it only cis and trans products for E1? You can have cis and trans products for any elimination reaction. The only reason why I did not have cis trans isomerism for this guy right here is because, again, we have to have 2 different substituents on the side with the, we have to have one of the same on each side of the double bond, but then they have to be different on the other side. It's like we can't have 2 hydrogens to make cis and trans products. One of these hydrogens has to be something else, which is exactly what happened over here with this double bond. Okay? Does that make sense? Okay. So now, how many products were produced in this how many products were produced in this reaction, including stereoisomers? The answer is 5. No, we do not count Br as a product, Br minus, because if you think about it, we could also end up with HBr. We could end up with Br2. Like, it just depends on a lot of stuff. A lot of the times when we ask about products, we're asking about organic products and not these inorganic products. Okay? Okay, and so now when we get to the second question, we kind of have to understand, one, what this reaction was, SN2E2, SN1E1, and then we have to understand how the rate equation works. So the answer for this one is going to be also be C, because remember, we said this is going to be SN1/E1, and then the slow step of both SN1 and E1 is the removal of that leaving group and the production of that positive carbocation. Okay? A is wrong because it would sort of be, this would be the type of rate that we'd see for an SN2 or E2. This one's wrong because it doesn't even include the correct reactant. OH isn't one of our reactants. This one is wrong because while it is a step for E1 and SN1, it is not the slow step. So that's why C is our answer. Okay? If H2O was changed to negative OH, what would the reaction mechanism be? So essentially, we're changing from a weak acid, weak base to a weak acid, a weak nucleophile, weak base to a strong nucleophile and strong base. I probably
Okay.
should have added this. I should have also had SN2 plus E2 as a potential answer here, because this question was my fault. I should have made it a little bit more clear. But we're going from a weak nucleophile weak base to a strong nucleophile strong base. So technically it would be SN2 and E2. I just caught this, so I'm sorry. So this would be C and D. But I think what I was thinking in this question is I was trying to make it SN2. I think I was trying to make it SN2. So let's also think, what if we made negative OH instead of having negative OH? We had tert butoxy. Now we have a strong, bulky base, so it's going to prefer E2. So the answer to this guy is actually SN2 and E2. I made a typo over here, and I'm sorry. I'm crying. Okay? But if you chose SN2 or E2, both of those would be correct. All right, so let's continue on. Oh, I just answered this question. That shows you how predictable I am. So tert butoxy, that was what I just drew here. So it's a strong, bulky base, so it's going to be E2. Okay? And again, SN1 and E1 are always going to occur together with weak acid, weak bases. SN2, as far as secondary goes, it's going to use a small nucleophile, small base, and it's also going to perform E2. Okay? So 4, answer is D. Okay. So what will be the elimination products of this reaction? So to do this, what we have to do is we have to recognize, is this going to be a E1 or E2? So specifically, this question asks for elimination products. So we can sort of ignore any substitution products that we might get. So we see here, we have a secondary alkyl halide, and we have a weak base, we have a weak base and a weak nucleophile. So what we're going to do here is we're going to draw out our first step. It is the halogen leaving. So we end up with the positive charge right here. And notice we have a secondary carbocation next to a tertiary carbon. So we're going to do a hydride shift, as we talked about before. That hydrogen is going to move there. And then we end up with Then we end up with our carbocation being right here. And so then our elimination products, I guess, would be this guy and this guy. And remember, if I had another product like this here, these two are essentially the same. So I only need to list them once. So now we want to match these products with one of these answers here, and we see it matches with B. So our answer here is B. And yes, Connor, you got that one right. See, all of these questions are meant to sort of test you, and they're honestly filled with traps that are meant to get you wrong. Because, like I said before, oops, like this question says here, it says tert butoxy instead of drawing it out. Wait, I am confused with the double bond in the first part of the answer. Oh, okay. Let me just undo. Okay. Let me scroll down a little bit so everything matches up again. Okay. There we go. Okay, so first step, we get rid of the alkyl halide. We make our carbocation. Then we see we have a secondary carbocation right next to a tertiary carbocation. So we do a 1,2 hydride shift. And so now we have our alpha carbon. This is our alpha carbon. So we have a beta carbon right here, a beta carbon right here, and then a beta carbon right here. And we can see here that beta 1 and beta 2, they're going to make the same two products. And then beta 3 is going to make this last product right here. And so since beta 2 and beta 1 will make the same product, we're just going to list that product once. In this case, I listed it like this one. Okay, how do you determine if a base is weak or strong? Generally, weak bases are going to be neutrally charged, and strong bases will be negatively charged. That is not like a hard and fast rule, but for this class, 90% of the time, if you see a negative charge, it's going to be a strong base, strong nucleophile. If you see a neutral charge, it's going to be weak. Okay? Okay. So let's just do one bonus here. If I were to do the SN1 reaction, if I were to do the SN1 reaction, I would want to draw in the actual stereochemistry here, because if I did the SN1 reaction, we would still have the same hydride shift. So I'm going to skip what I did before. I'm going to put the hydrogen, the positive charge here, and then have my two hydrogens here and all that stuff. So I just skipped the hydride shifts to save some time. So now if I were to do the SN1 reaction, we're going to have CH3OH. The CH3OH is going to attack that positive charge. Then we end up with two possible products here for the SN1. We have one where we have our methyl group in the front and our OCH3H group in the back. Or another one where we have our methyl group in the back and our OCH3 group in the front. And also, the last step to an SN1 reaction is generally going to be deprotonation. And usually that deprotonation is going to be done by the leaving group that we had before. So Cl negative would grab onto that hydrogen right here and right here. And then that oxygen would gain those two electrons, and then it would be happily neutrally charged. So these would be the SN1 mechanism, the SN1 products. So we can see here that we get two SN1 products and two elimination products. So we get 4 products total. It's just in this case, I only asked for elimination. Okay? All right. Oops, let me scroll back here. So what will be the major product for this reaction? So now we see something a little bit different. So it's the same reaction as before, or not the same reaction, but it's the same substrate as before, except now we have this strong bulky base. Whenever you see a strong bulky base, you should be thinking, oh, this is going to be E2. So everything happens in one step. The Cl leaves, and then our O negative is going to attack one of our beta carbons. However, notice here, how this is a strong, bulky base. It's bulky. So it's not going to attack this one right here to make our major product. Instead, it's going to attack this less substituted carbon over here to make the major product. So that means that our product is going to look like this. Okay? So that means our product is D here. Okay? Does that make sense to everybody? And notice here, this says major product. So the difference between this question and the question from before is that this question asks for the major product only. So it's only asking you for one product. However, the question before was asking you for all of the elimination products. All right? Okay. So let's go back here. Oops, I just jumped ahead. Rank the following alkyl halides in order of increasing reactivity for an E2 reaction. So remember, for an E2 reaction, E2 loves tertiary. So
Es B, A, C.
yes. So it's going to be BAC, which is B. Okay? All right. So let's continue on. Oops. So this next question sort of has to do with making an alkyne. So which of the following will not produce an alkyne through elimination reactions? So like I said before, we have to have either a bisenyl dihalide or geminal dihalide. We can see here, this one is a vicinal dihalide. This one's a geminal dihalide, which leaves these two as our suspects. However, look at D. We can see that it's sort of like it's already gone through the first step of E2. It's already done E2 once, so it could do E2 again and end up with an alkyne. So this one works as well. So the only one that does not work is A. All right?
Can you explain which the vicinal and the other thing?
Yes. The vicinal, and let me zoom in a little bit just so for the sake of clarity. So when I'm talking about vicinal and geminal dihalides, all this means is I have an R group, like a carbon chain, with two halogens on it. That's what a dihalide is. And so now let's talk about vicinal versus geminal. Vicinal means they're in the same vicinity, so they're going to be on carbons right next to each other. So X will represent my halogens here, okay? And then when we're talking about geminal dihalides, they're twins. They're going to share the same carbon. I always thought this of like Geminis. Gemini means twins. It's the whole zodiac and all that stuff. So we can see here that these two halogens are twins, and so they're on the same carbon, so they're known as geminal dihalide. Okay? And so vicinal and geminal dihalides will go through E2 twice to create an alkyne. Okay? So also that first step is going to make one double bond, and then one of the halogens are going to stay, and then this is what D is. Okay? That's what D is. D is, it's already gone through elimination once, it just has to do it again. So we can see here that vicinal dihalides and geminal dihalides can both go through E2 twice in order to create alkynes. So we see here C is a vicinal dihalide and B is a geminal dihalide, and A is neither. So A is the only one to not be able to make an alkyne, and that's what this question is asking. Not which one is able, it's which one will not produce an alkyne. Okay, does that make sense? Did that help any questions about vicinal versus geminal and all that stuff?
Yes, thank you.
All right, perfect. Okay. So what base will cause the Hoffman product to be formed? This one is tricky, obviously, because instead of drawing out the actual basis, I wrote out the names. So this forces you to sort of understand what all these words mean. But like I've been sort of drilling it into you this whole time, tert-butoxy is a bulky base that likes the Hoffman product. Ethoxy would be an ethyl group attached to an oxygen. So ethyl is the 1, 2. Oxy is the O negative. Hydroxide, that's just OH negative. And then ammonia is NH3. All of these are good bases. What are the names of the bases that we should memorize? Honestly, all of these bases are pretty common. You should be able to read something and sort of decipher what it is. Like if I said methoxy, you should be able to sort of think it through and be like, oh, I know meth means we have one carbon. Oxy means it's attached to an oxygen. So that means our methoxy must look like this. Okay? Does that make sense? And also, I would say memorize tert-butoxy. Most of the time, it will be drawn for you. I just know some professors will have you or will force you to know the names, so I kind of want to gear you guys up for that as well. Okay? All right, perfect.
Sorry, Casey. So for the Hoffman product, isn't that the one that's less, that prefers less substituted? Like,
Zeitstev prefers less substituted because remember the car example. Zeitstev is more stable.
oh yeah,
That
sorry.
is not wrong. That was the wrong thing. Zeitstev is more, so like this would be a Zeitstev product and then this would be a Hoffman product. The
So,
Zeitstev product has more substituents attached to it, so it likes a smaller base. Hoffman has more or less substituents, so it prefers the bulky base like tertbutoxy. Okay, does that make sense?
yeah, so I'm sorry. What I meant was like, I'm sorry. So for the site sieve, that one prefers the major product. Hoffman prefers the minor product. Is that okay? Is that right?
Well, I mean, sometimes, okay, so most of the time, yes, Zeitstev will be the major, Hoffman will be the minor. However, the Hoffman will be the major product if we use a big bulky base like tertbutoxy.
Okay.
Okay, does that make sense?
Yes.
Okay, so now here's an easy one to sort of let this one just sort of pull it out here. Organize these alkenes from most to least stable. So all we have to do is we have to find the most substituted, or the one with the most substituents, in order, and then compare it to those with the less substituents. So I'm going to go ahead and number these. So A has 3 substituents, B has 1, C has 2, D has 2. So obviously A is going to be the most stable and B is going to be the least stable. So now I'm going to look through these and see uh, sorry, we're going to see which one of these starts with A because we're going from most to least. So it's not going to be B, it's not going to be D. And then we have to see which one's going to end with B. So it's not going to be A or B or C. Or I mean, it's not C, but D. So it has to be C. So I didn't even really have to compare C and D. So like this is sort of a strategy that you can do to get through stuff really fast. Because I know you guys have like limited time to take these tests. So I kind of want to sort of help you find strategies that will help you take it faster. And then if you had time, you'd be able to see that D is trans and C is cis. So D is going to be more stable than C. So it's going to go A, D, C, B, which is what C is. Okay? All right, and so then that's the end of the questions as far as chapter 8 goes, the elimination chapter. I tried to make these as tricky as possible in order to sort of help you. So will trans always be more stable? Not necessarily, but in this case, we want to keep the big groups away from each other. So like let's say that instead of being cis or trans, we had an ethyl group right here. So this would still sort of be considered trans because we have a methyl group trans to another methyl group, but this would sort of be considered less stable than something that would have the ethyl group or have the methyl group cis. And this is because we're keeping the big groups away from each other. And again, I'm going to talk about this a little bit more when we get into chapter 10. Okay, does that make sense? Okay, perfect. Are there any more questions before we move on to chapter 9? All right. Okay, so now we'll be going into chapter 9, alcohols, ethers, epoxides, thiols, and sulfides, and then after chapter 9, we will go through chapter 10. I just don't have any questions prepared for chapter 10 because I want to spend a little bit more time on explanations for that chapter rather than questions, because I know that in class you guys haven't gone over it quite yet, so I kind of want to help you understand it before I bombard you with a bunch of different questions, okay? But first, let's go through chapter 9, for which I do have a few questions prepared. Okay, so talking about alcohols, ethers, and epoxides, here are the general structures of those things. So alcohols generally just are have an sp3 are an OH group attached to an sp3 hybridized carbon. This can be a secondary carbon, a primary carbon, or a tertiary carbon, as long as that carbon is sp3. And the reason why we specify that it's going to be sp3 is because we end up talking about a different functional group later in Orgo 1 and then in Orgo 2 with a double bond to an oxygen and then a single bond to an OH, where this carbon here is an sp2 carbon. And so then this guy here, this guy is not considered an alcohol. It's something called a carboxylic acid. And so that's why we want to specify that an alcohol is an OH group, a hydroxy group, bonded to an sp3 hybridized carbon. Okay? And so now an ether is sort of the same thing. It's an oxygen bound to two different R groups, so it's bound to two different carbons on either side. So these carbon chains can be however long, so this could be like a CH3, this could be an ethyl group, it just goes on and on. And epoxides, they're probably one of the more interesting. This is probably my favorite functional group. They call me a nerd, whatever. I just think it looks really cool. It's two carbons connected to an oxygen in a triangle shape with like little legs. And then what these legs are showing, they're showing that these two carbons are sp3 hybridized, and thus they have tetrahedral geometry. And so then that's what these little legs are showing and why it's important to show them. Okay? And epoxides, they don't have to be attached to only methyl groups. We can have, a lot of the time, you're going to see epoxides that look like this, where they're attached to a cyclohexane, or you can see an epoxide where it's not even attached to anything on one side, and it's got like an ethyl group right here, and then a methyl group right here. So as long as you have that center triangle, it's going to be an epoxide. Okay? All right. So let's scroll down. So let's start with alcohols. And how do we sort of describe alcohols? We describe them in the same way that we describe hydrogens. They're either going to be a primary, secondary, or tertiary alcohol. And this depends on what kind of carbon it's attached to. So we can see here that when a carbon or when a hydroxy group, which is the OH group, is attached to a primary carbon, it's known as a primary alcohol. When it's attached to a secondary carbon, it's known as a secondary alcohol, and then so on with the tertiary, okay? And then we can see in this example it a little bit clearer. So we see that this first alcohol right here, it's attached to a secondary carbon, so it's going to be a secondary alcohol. We can see that this carbon here is attached to a tertiary, or I'm sorry, this hydroxy group here is attached to a tertiary carbon, so it's known as a tertiary alcohol. And then we can see that this guy is attached to a primary carbon, which is attached to, or a primary carbon, so it's a primary alcohol. And you may be saying, but that alcohol is attached to an sp2 carbon. Well, no, because and yes, this confused me too, because I was like, wait a second, there's an sp2 carbon right there. But what's different is this alcohol, this OH group, is attached to a carbon that is attached to that sp2 carbon. So if this confused you, like it did me when I first saw it, don't worry. It's just the nature of organic chemistry. Sometimes the drawings get a little bit confusing and they're hard to understand, but once you break it down, it's a lot simpler. And that's why I also sort of recommend, if you have like a big thing like this, and it's asking you to say, what kind of alcohols are these? I would definitely recommend drawing in those hydrogens that you don't see. So like we see here, like, oh, this carbon has to have 4 bonds, so it has to have 2 hydrogen bonds. Oh, this guy has 4 bonds, it's sp3. And so then that confirms that it's an alcohol and all of that stuff. Okay?
So alcohols always have to be sp3s.
Yes, exactly. The hydroxy group has to be connected to an sp3 carbon because of different functional groups that we will talk about a little bit later. Okay?
Thank you.
No problem. And so now let's talk a little bit about alcohol nomenclature. So when we're talking about nomenclature, it's essentially the same thing as when we talk about like alkyl halide nomenclature. We're first going to find the parent chain. So in this case, it would be this central carbon chain here. Then we're going to find the substituents. Here's a hydroxy group, here's a methyl group, and then we're going to number it. So in this case, there are 2 ways we can number it. 1, 2, 3, 4, 5, 6. We're going to call this numbering system the top numbering system. And here's 1, 2, 3, 4, 5, 6. And we're going to call this second numbering system the bottom numbering system. Okay? And so we can see here that both of these numbering systems put a substituent on 3 and a substituent on 4. So now we have to decide which one we prefer. And then we have to talk about now is something called the priority system. So certain groups are going to have higher priorities than others. So like in this case, hydroxy groups, alcohol groups, have a higher priority than alkyl groups, which is this methyl group here. So what that means is we're going to prefer the bottom numbering system in order to give the groups with higher priority a lower number. So this guy is going to have a 4-methyl instead of a 3-methyl, okay? And so then now you may be asking me, how do we include the OH group? Well, instead of including the OH group as a prefix, we're going to include it as a suffix. So the parent name, which is going to be hex, so hexane, and then we're going to add a dash, and then we're going to say 3-ol, because this OL is sort of representing the OH group, and then the 3 is telling us where it is. So the whole name would be 4-methyl hexane 3-ol. Okay?
So we don't take the E off. I thought we always like drop the E.
So sometimes okay, so this is sort of like a point of contention. Sometimes people drop the E, sometimes they don't. I would say go ahead and drop the E for these, and I'll explain why dropping the E is sort of like contentious. It's because whenever we have something with like a double bond in it, so instead of being hexane, or instead of hexane, like if we had a double bond, it would be hexene. And so then it would be hexenol.
I
And so,
saw.
go
Oh,
ahead.
sorry.
No, go ahead.
I saw like in some practice problems in the book that when there was like more than one like OH group,
You call it a diol.
Yeah, and then like you drop the. Never mind.
It's
Forget
fine. We'll get into that in a little bit, I promise. And somebody asked in the chat, can we also name it as 4-methylhexanol since there's only one alcohol? No, because if we named it 4-methylhexanol, that sort of implies that this OH group is on 1. If we named it 4-methylhexanol without telling anybody where the OH group is, then we wouldn't know where it is. The only time that we'd really do that, drop the number for the OH group, is when we have a cyclo. And I'll explain why when we get there. But yes, okay, so drop the E. So if we have hexane 3-ol, drop the E. I would in the test and everything. It's just sort of habit for me to write it with the E because certain professors like it different ways. Dr. Daddy likes it this way though. Okay? And then somebody said, can we also name it 4-methyl-3-hexanol? Technically, yes, but I think this way is preferred just because for the sake of clarity, we kind of want to keep numbers next to their sort of functional groups. So we keep 4 next to methyl. So we also want to keep 3 next to all because that's sort of the representation of the OH group. Because in the textbook, it's like the way I wrote it. I mean, it's like there's a couple different ways to write these different names, and I prefer a way that's a little bit different than the textbook way, but both ways are technically correct. I just like this way better because it keeps the numbers next to the substituents. And I think Dr. Daddy mentioned in class that he prefers it that way too, but both ways are correct. Okay? Okay, go
Why
ahead.
is alcohol in a 4 and not in a 3? It's located in the parent chain on 3.
Yeah, it's 1, 2, 3, 4. It's 4-methyl. It's 4-methyl-hexane 3-ol.
3-ol.
And yes.
Got it. Sorry.
No, you're fine. You're fine. You're totally fine. Okay. So now here we're getting to an example where sometimes you can drop the 1 or you can drop the number because when we're talking about hexanes, or we're talking about cyclos rather, cyclohexane in this case, when the way that we number cyclos is we start from any carbon that we choose and then we number it clockwise or counterclockwise. So like 1, 2, 3, 4, 5, 6. And since we want to give everything the lowest number possible, and since OH is going to be the highest priority in both of these cases, sometimes people will drop the 1 and just put hexanol. I usually keep the 1 in, 1 for my own sake because I don't want to confuse myself, 2 for your sake for clarity purposes, and 3 just because I like to keep things consistent when I'm naming stuff. But you can drop the 1 if you're in a cyclic compound. If you're in a linear compound like this guy, you cannot drop the 1 Because if I just said it was so this would be cyclohexanol. If I just said this was like 1, 2, 3, 4, 5. If I just said this was pentanol, that does not tell me where the OH is. Because we can number this either 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. We can't make any carbon that we want 1 like we can with cyclos, which is why sometimes you'll see the 1 all dropped when we're talking about cyclos. Okay, but I usually keep it in just for sake of clarity and just to keep things consistent, because again, it can get confusing because you think, oh, since there's only 1 alcohol, we can drop the number, but that's not necessarily true. All right, so let's look at this one. Okay, again, you want to give OH the priority, so you want to give it a lower number than these alkyl groups, and so we're going to number it 1, 2, 3, 4, 5, 6. Okay. And so then we see we have 3, 3 dimethyl hexane, or sorry, that should be cyclo. Sorry. Cyclohexane 1 all. Again, you don't have to put the 1. I like to do it just for sake of clarity. And I'm missing something here. I'm missing the stereochemistry at 1. 3 is not a stereocenter, so we don't have to give it we don't have to give it a conformation, but 1 we have to. So we say it's okay. So group 1 is OH, group 2 is this group on the left, group 3 is this group on the right. 1, 2, 3. But that's not quite right, because our highest priority, rather the lowest priority is not on this dashed wedge. So what I usually do is I redraw this in its tetrahedral form, because again, while you can just swap it, sometimes that's not always the case. So I'm gonna make 3 up top, 2 over here, 1 right here, and then 4 right here. Because what I'm doing here is I'm drawing it tetrahedral, and I'm giving each one of these lines a different conformation or a different priority. I'm just sort of taking this whole structure and rewriting it so it's easier for me to see. And somebody asked, how do you know whether or not you have to write it with R or S? Whenever you have a stereocenter that's defined, so in this case we see OH is on a dashed wedge, and that's defined, so we have to do R or S, okay? So what I'm going to do here, if you haven't watched my video on stereochemistry and everything, I would if you're confused by this. But what I'm going to do is I'm going to pick it up. I'm going to twirl it around. So 4 goes where 1 is, 1 goes where 2 is, 2 goes where 4 is. And we end up with, got to redraw it, 4 right here, 2 right here, 1 right here, 3 right here. And we see, okay, this is going to be R. So I'm going to put R at the front, R-3,3-dimethylcyclohexane 1 all. Okay, and so then that's the full name. Again, you don't have to put 1 all, but I like to just to keep things consistent. Okay. So when we're naming things with diol or triol or anything, this is exactly the same when we name things with dimethyl or, oh, I'm sorry. I think I forgot to put, no, I did, sorry. I thought I forgot to put dimethyl here, but we're good. So anyways, when we have 2 methyl groups, 3 methyl groups, we call it dimethyl or trimethyl. It's the same thing here. If you have 2 alcohol groups, we're going to say diol, where it's like the di is in front of the ol because we're having 2 alls. So diol, triol's the same way, tetraol is the same way, but I don't think you're going to see over anything more than triol. Okay? And so then these are just more examples. I kind of want to get into more reactions soon, but let's just continue with the naming. So when we're naming ethers, there are a few different ways that we can name them. Either you can name each substituent on either side. So like in this case, you have ethyl methyl ether because we have an ether. We have an ethyl on one side of the ether and a methyl on the other side of the ether. Here, tert-butyl methyl ether. We have a tert-butyl on one side, a methyl on another side. But we can also name it finding the quote-unquote parent chain, which is the longest chain off of that oxygen. In this case, that would be pentane. And then we see that we take whatever chain is here. So the shorter chain, we have 1, 2. So it's going to be eth, and then an oxygen attached to it, oxy. So remember before, we were talking about methoxy, ethoxy, tertbutoxy, all of that stuff. It just means we take the front part of the name, which is the base name for that number of carbons, and then add oxy to the end, telling us there's an oxygen there. So it's sort of the same type of naming. So let's say that we have this example right here. Let's say we have this guy right here and then his parent chain right here. So we can see here that we have 1, 2, 3, 4, 5 carbons on this side, and then 1, 2 in one chain on this side, and then 1, 2 on another chain. So that means that 5 is going to be our longest parent chain. So this is going to be pentane. And we can see that this whole thing, this is an isobutyl group. So we're going to call this isobutoxy pentane. Okay? And since there's a space in between those words, we're not going to put a dash. Okay. Where are you getting butoxy? Oh, I'm sorry. It should be isopropoxy. I was thinking about It should be isopropoxy. I was thinking about tertbutoxy again because that's my favorite bulky base. So it should have been isopropoxy pentane. I'm so sorry. Okay. So properties of alcohols. So now we're getting into some of the more interesting stuff because now we're going to be talking about how alcohols will react and how they will act in certain situations. And so we can see here that again, steric hindrance plays a role in the hydrogen bonding. So the more steric hindrance we have, the less ability it has to hydrogen bond. And so we can think of this as there's less intermolecular forces as there's more steric hindrance. So we can see here that the boiling point is going to increase as the ability to hydrogen bond increases as the steric hindrance decreases, okay? All right, so now let's talk a little bit about crown ethers. These can be a little bit tricky to understand at first, but the reason why we want to understand crown ethers is because generally we are going to add a crown ether to a non-polar solvent in order to do stuff like substitution and elimination reactions. So usually for elimination reactions, substitution reactions, all of that stuff, we're going to use a polar solvent, either polar protic or polar aprotic. If we don't have a polar solvent, which is a lot of the time in your body, you have non-polar solvents, we're going to add crown ethers in order to cause that reaction to occur. And so then what those crown ethers will do is they'll take ions, specifically cations, so like lithium plus potassium plus that sort of thing, and they'll sort of trap them within that nonpolar solvent. And to name these things, essentially you have the general anatomy of the name, X crown Y, where X is the total number of atoms in the crown, Y is the total number of oxygens in the crown. So if we take this first example here, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's where the 12 comes from. And then we have 1, 2, 3, 4 oxygens. That's where the 4 comes from. And so on with all of these, okay? So crown ethers, they look scary, but they're really easy to name, especially compared to some other stuff. And again, talking about here, this is talking about why we use crown ethers and all of that. I'm sure there was like a section in your book talking about how it's used in the body. I don't remember if that was in this section or a different section, but yeah. Okay, so now we're talking about the preparation of alcohols and ethers. So the main way that we make alcohols and ethers is just by substitution reactions. We take an alkyl halide, and then we substitute either OH or OR. This R can be anything as long as it's not sterically hindering. So this O could be like an ethoxy group or a propoxy, okay? So that's how we make ethers. And so let's talk a little bit more about ethers, because this SN2 reaction for alcohols is sort of self-explanatory, but ethers can be a little bit more tricky. So remember, ethers have one R side and then another R side. And if we want to make an ether, we're just going to do a substitution reaction with one of these sides. So like either, let me highlight, either this ethoxy or with this, 1, 2, 3, propoxy. But how do we know which one is going to be the alkyl halide and which one is going to be our nucleophile? So we turn to something called Williamson ether synthesis. And so then this is sort of just explaining that there are two different ways to make a single ether, because there are two possible nucleophiles and two possible alkyl halides. But we also have to remember that the reaction mechanism is SN2. So this, while both of them seem sort of sterically hindered, or they could be sterically hindered, we are going to sort of prefer that the nucleophile, aka the one with the oxygen on it, is more sterically hindered than the alkyl halide. That is just the general rule. And also this is showing us how we turn alcohols into sort of oxys. So we add a really strong base in order to deprotonate that alcohol in order to make our nucleophile here to do our Williamson ether synthesis. Okay?
I'm sorry, which one was better? It was path B, right?
Yes, path B, because again, while this is SN2, and while either way we're going to get something that's sterically hindered, we are going to prefer that the alkyl halide is not sterically hindered. Okay, does that make sense?
Yes, thank you.
All right, perfect. Okay. So now let's talk about the preparation of epoxides. Okay, so let's talk about what a halohydrin is. So this name is probably really confusing because you've never seen it before, but halo means we have a halogen. Hydrin means we have a hydroxy group, right here. So that X is our halo group. This is our hydrin group. Okay, so again, just breaking down names to see each part of them to see what's going on with them. Okay. And so essentially what happens with making an epoxide, this is sort of spelled wrong here, there should be an O here. Making an epoxide, essentially what happens is an intramolecular SN2 reaction. Because we can see here what happens is we have a base deprotonate this hydrogen here. We deprotonate the alcohol, and then what happens is, look, we have a good leaving group here and a good nucleophile right here. So what's going to happen is this leaving group is going to leave, and this nucleophile, aka the oxygen here, is going to replace that leaving group and then make our epoxide. Okay? So all of these mechanisms are really important, but this one is probably one of the more important ones because it can be really confusing, and there are going to be questions on ACS if you end up taking it, and maybe on the test. I'm not 100% sure. Again, I don't know what the test is before you guys take it. Okay? All right. So reactions general features. So the general idea behind alcohol reactions is we have to make the alcohol a good leaving group. Because remember, if we compare OH as a leaving group with OH2 as a leaving group, OH2 makes a much better leaving group than OH. So generally, if we're going to do like a replacement reaction, a substitution reaction, we are going to need HX, which is just H and any halogen, which is just like hydrobromic acid, all of that stuff. So what happens here is that there's the X or the halogen leaves the hydrogen as the hydrogen is grabbed by the oxygen. Then we end up with OH2. That OH2 is a leaving group, and it can be replaced by the halogen from before. Okay? We can also do beta elimination with these things. So what I just talked about was the nucleophilic substitution. We can also do beta elimination, and this is usually done by using a strong acid. Again, I'm going to talk about this more later. This is just showing you like the general overview. And so then we see here that we can also attack epoxides and do something called an epoxide ring opening, where we just open the ring. Okay? So the hydration or the dehydration of alcohols. Dehydration, we've all heard it before. We're losing a water molecule. Okay? So let me show you the mechanism. I don't know if it shows it on the next page. It does. Okay. So what we're doing here in this mechanism is we're taking H2SO4. That's what this is. The way that it's going to be commonly drawn in the book on these PowerPoints, how I'm going to draw it, H2SO4, it's sort of a a smaller version of its Lewis acid structure. So this Lewis acid looks like this. But what we're really interested about is this OH bond right here, which is the thing that reacts, okay? So that's why we draw it as H bonded to OSO3H, okay? So the whole mechanism of this is first the OH grabs the hydrogen from the acid, because again, acids really want to give away their hydrogens, and we're left with a negatively charged acid and a really good leaving group on our alkyl group. So then we have that leaving group leave, and we make a carbocation. Again, notice we're making a carbocation so we can undergo rearrangement. And then we use our acid from before, our conjugate base from before. It will grab the hydrogen from the carbocation, and we just undergo elimination just like before. Notice here how the H2SO4 remains unchanged between the beginning and the end of the reaction. So that means that H2SO4 is a catalyst for this reaction. All right? Okay. So here's some more examples. So like we can see here that the first step is 1, to protonate the alcohol, 2, have the leaving group leave, at least for this first. Okay, so dehydration of alcohols, when we use a tertiary alcohol, then it's going to go through SN, or not SN1, but E1. When we have primary, it's going to go through E2. And if we have a secondary, it's sort of kind of assumed that we're going to be doing E1 over E2 for reasons that I am not advanced enough to know. Okay? All right. This could be seen in some of the worksheets that we did before. Okay, so let's continue on. So again, if we make a carbocation, then we can undergo a carbocation rearrangement with either a 1,2 methyl shift or a 1,2 hydride shift. So this is just demonstrating that again for us in case you forgot from last time. Okay, we can also do dehydration with POCl3. I would not recommend memorizing this mechanism. The one from before is important to memorize, important to know. This one's less important to know by heart. It's more important to understand that POCl3 and pyridine will end up dehydrating an alcohol. Okay? All right. So alkyl halides formation. So again, it's going to be sort of what I talked about a little bit earlier, where we have a strong acid in the form of HBr, HCl, HI, any of those. And what happens is that the alcohol is going to get protonated by that hydrogen. The halogen is going to leave. Then we end up with R attached to OH2 plus, which is a good leaving group, and a strong nucleophile, and then that OH2 is going to be replaced by the X, and we end up with RX over ROH, okay? So there should be a mechanism a little bit further. Yep, here we go. So what happens here is generally this is going, again, this follows the same sort of rules that we did before with the dehydration, where if it's primary, then it's going to be SN2. If it's secondary or tertiary, it's going to be SN1. And then if it's secondary, we're going to kind of assume that it's going to be SN1. Okay? All right. But it can be SN2 at times. There's also some certain special reactants that will turn it into, that will do the replacement. So sometimes you'll see HCl on its own, or you'll see zinc Cl2 in order to do the reaction. So what happens here is either you can use this sort of diagram is kind of confusing, but you could use HCl or you can use zinc chloride to make this alkyl halide, this chlorine alkyl halide. Okay, so you can see here's sort of the quote unquote mechanism, but it's essentially the same thing that happens with the HCl. Instead of using HCl as our instead of using H as our attacking group, we use sort of the zinc instead. But just know that if you see zinc chloride, then that's going to replace an alcohol with a Cl. Okay. So another special reactant, so similar to POCl3, we can use SOCl2 in order to replace OH with a chlorine. Yes, this is a lot of reactions. I'm going to do my best to get a list of all the different reactions for you guys, if I can before the test, but there's a lot of them. And I'm going to try and get Dr. Daddy to post it as an announcement, or I'll send it to people who can send it to their friends and all of that stuff. But again, these are a lot of reactions. I'm going to do my best to sort of get them all in one place for you guys. But just know that an alcohol with SOCl2 will replace the OH with a Cl group. Okay? All right. And then PBr3 does the same thing, but with bromine. These reactions here, I wouldn't recommend memorizing the mechanism. Rather, I would recommend what reactants do what, especially when thinking about SOCl2 and PBr3. And somebody asked, could we send it to the GroupMe if you do make it? Of course, you can send anything that I make to the GroupMe. I don't mind. And then also, another thing that you can do is you can convert OH to something called tosylate. So if you see TSCl, this guy here, what's going to happen is essentially the same thing as what we did with like something like HCl, except the H is actually going to be replaced by TS. And then we end up with OTS, which is then a good leaving group, and then we can do any SN2 reactions. Okay, so this is sort of like this is sort of like opening up the alcohol to different types of replacement reactions, substitution reactions, without using HCl or like an acid. And this is sort of preferred sometimes because, again, think about in lab, if you're doing a reaction and you can try to avoid using sulfuric acid, that's mostly preferred. So like this is something that we have to know for lab. And also we can see here, it's useful for doing replacements without needing to use HCl or HBr. You can skip a whole step, okay? Okay. So now let's talk about reactions of ethers, acidic cleavage. So all this means is if you have two HXs, so like two alkyl or two hydrobromic acids, all that stuff, then what's going to happen is this ether is going to split in half with this oxygen on either side being replaced by Br or whatever alkyl halide that you're using. So we can see here that we need two, because what we're going to do is we're sort of converting this lone oxygen into an H2O, which comes from the two equivalents of that acid, and then we're making two alkyl halides by replacing that oxygen, in which those two halogens come from that two equivalent HBr, HCl, HI. Okay? And so essentially what happens in the mechanism is we kind of do what we did before twice. So we make the ether, but instead of having a OH group, we have a OR group. So what happens is you protonate this oxygen, make it into a good leaving group, it leaves, and then it's replaced by the halogen from before. Okay? And so then the same thing happens again, but now it's sort of something that we're more familiar with, where we're using the HX with an alcohol itself, okay? All right. So thiols. So this is a little bit different from the rest of the chapter that we've been discussing, but the whole reason that we talk about thiols is because sulfur has very similar connections to oxygen, and we can see that in the periodic table because they're in the same row. Oxygen is right above sulfur. Okay, so we can see here that, and then also the mercapto group, the SH group, is similar to the hydroxy group. However, we can see here that ethanol has a much higher boiling point than ethane thiol. And because ethanol has hydrogen bonding and ethane thiol does not. Okay? And usually these things with sulfur are going to have like a very strong odor and sort of be very very distinctive. Okay? So we can see thiols go through much of the same reactions as alcohols. So you can see here that to make a thiol, we're just going to do an SN2 reaction with an alkyl halide and an SH group instead of an OH group here. And again, and then something that's interesting about these thiols is we can make something called a disulfide bridge, which happens because we take away these hydrogens using bromine or iodine, and then two equivalents of those substrates come together to make this new bond right here. And then we can break that bond as well with zinc and hydrochloric acid. And again, this stuff, I personally find it less important than the alcohol stuff. But again, you should know how to do it, especially because these disulfide bridges occur a lot in the human body. So if you want to go into like med school or research about this stuff, this is really important to know. Okay. And so essentially, a sulfide is the ether version of the sulfur group. So we just have an S with two groups on either side of it, and we're essentially going to be naming it the same way that we name ethers. Sec-butyl, this is our sec-butyl. Ethyl, ethyl. Sulfide, there's the S in the middle. So we're naming it just like any other, any ether, but instead of having ether at the end, we have sulfide at the end. Okay? Okay, so sulfides preparation, again, all that's going to occur is sort of a replacement reaction where we take a strong base, which is going to deprotonate this mercapto group, and then the R of the RX group is then going to replace it. Okay, so again, this mechanism is important to know, but it's really similar to the other mechanisms. So it's like really similar to stuff that we've seen before, like how do we make ethers, that sort of thing. Reaction to sulfides. So this is just, again, similar to ethers. We start with we are similar to alcohols becoming ethers. We start with a thiol, then we get rid of that hydrogen, making this into a good nucleophile. So this is a little bit different from the OH stuff. But then all we do is another SN2 reaction to make ethyl propyl sulfide to make our sulfides. This again, all of these reactions are just stuff that you sort of have to practice and study. Again, I'm working on making a document for all of you that has all of the reactions. Okay. So here comes one of the more important bits of this reaction, or this chapter, is the opening of epoxide rings. And the reason why this is so important is because the next chapter, Alkenes, chapter 10, has a lot of stuff to do with epoxides as far as adding OH groups to a double bond and that sort of thing. So there are two ways that we can open epoxide ring. The first one that's shown here is using a nucleophile. And all that happens is the nucleophile is going to attack this strain carbon because it has a lot of ring strain, because it's being forced into that position. So it has a lot of ring strain, and it's also partially positive because this oxygen is pulling all of the negative charges towards itself. Okay? So then that nucleophile attacks that carbon. The oxygen, this bond breaks, goes onto the oxygen. The oxygen attracts a new hydrogen, and we end up with this guy right here. We end up with an alcohol. In addition, there's going to end up, the nucleophile is going to end up as far away as possible from the O group because we're doing a SN2 reaction. And what this means is that the nucleophile, so you see here, I'm going to zoom in really quickly. We can see here that this oxygen is pointed up on this carbon right here, and then when the nucleophile attaches, it's now pointing down. This will also happen if, let's say that instead of having lines here, we have a solid wedge here, solid wedge here. This nucleophile would be on a dashed wedge. Okay? So, and also one thing to note here is that the nucleophile will always attack at the less substituted carbon for this reaction. Now let's talk about the acid catalyzed epoxide opening. So what happens first is we get the hydrogen. So before, the hydrogen, the proton attack was added last. But in the acid catalyzed epoxide opening, the hydrogen is added first, and we end up with this ion first. And then the leaving group, quote unquote, which is this OH group leaves, and the nucleophile attacks. Okay? What's also interesting about this is that the nucleophile is going to end up attacking at the more substituted carbon because of the stability of the transition state. Also, another thing I want to say is that stereochemistry is still inverted in this case because again, we're going through an SN2 reaction. Okay? Okay. So we can see here that the two different types of epoxide openings, this one is a nucleophile driven one, and this is an acid catalyzed one. So the nucleophile driven one puts this OCH3 on the less substituted carbon right here. Whereas the acid driven one, the acid catalyzed one, puts this CH3OH on the more substituted carbon. Okay, does that make sense? And so then that's the base difference between these two epoxide openings, these two types of epoxide openings. And I think that's about it for chapter 10. Are there any questions before I leave you to work on the questions that I made?
Can you just show, like, for that right there, how, like, you can open the ring to draw, like, the 1, 2, 3, like.
Yes. Okay. So I'm going to do this one right here. I'm going to do this bottom one. So what happens is we have HOSO3H. And then I'm going to go ahead and number these carbons. So this is going to be carbon 1, 2, 3. And then this one on this dashed wedge, I'm going to call this A. Okay? And so what's going to occur in this acid catalyzed opening, the oxygen is going to grab onto the hydrogen-oxygen bond is going to break, and then we end up with this guy right here, which is positively charged. Please forgive my drawing. And so then it looks like this, and if I number it, 1, 2, 3, A. And so then what happens is we have this weak nucleophile, weak base. So this is going to be an SN1 reaction. So what happens first is the leaving group leaves, and we end up with our carbocation. So like we can see here, like if I zoom out real quick, I'm going to clear this, and I'm going to zoom out and go to this one right here. We can see that when we do this, sorry, it's not SN1, it's SN2, sorry. When we do this transition state right here in this example, so pretend like instead of being Cl here, this is CH3OH. What happens here is that the CH3OH is going to attack that partially positive carbon. And then that mechanism would be shown over here. Okay, does that make sense? And so we can see here that if I number the carbons, 1, 2, 3, A, 1, 2, 3, A, 1, 2, 3, A, 1, 2, 3, A. All the stereochemistry stays the same except for the hydroxy group during the ring opening. Okay, does that make sense? Does that answer your question? Sort of thing?
Yes, thanks.
Okay, no problem. So I am now going to leave you guys to, let me stop sharing. And I'm going to leave you guys to do these practice questions. Again, these will be 11 through 20. Again, if you're on YouTube, just pause the video. So I'll see you after you guys are done. All right, it's time to go over these bad boys. So rank the following by boiling point. So if you recall, if we're looking at these intermolecular forces, we can see that hydrogen bonding, HB, is better than dipole-dipole action. So we can immediately see that D, since it doesn't have any hydrogen bonding, is going to have the worst boiling point. So it's going to be the first one that we see. I think there's there's another answer here. So we know that D is going to be the first one. So we can get rid of B and D. And so now let's look at these other ones. So we know that with increasing steric hindrance, there's a decreasing ability to hydrogen bond, and thus there's a decrease in boiling point. So the one with the highest boiling point should be A because it has the least steric hindrance. So let's look over here. Oh dear, I didn't put the right answer, huh? There was another typo. So, yeah. Yeah, I think, okay, so what happened here is I made a typo. I'm sorry. This one should have D and B flipped. So D would have been the answer. I have the answers over here to my right, but you can't see them. But it should have been D. I just made a typo, and I'm sorry about that. I'll probably go back and fix this before I post it in the YouTube description. So if you don't see an issue here, then that's great. But in this case, D would have the lowest boiling point because it doesn't have any hydrogen bonding, followed by B because it has the most steric hindrance, then C, and then A because A has the least steric hindrance. Again, I'm sorry about that typo. I can only catch so much at like midnight. So, because I wrote these last night. So, Did you guys, does that help you guys? Do you have any questions about this question? Or are you good? I'm just going to continue going over them. So name the following alcohol. So this one I did not make it I did not make it multiple choice because I wanted to give you guys practice in order to try and name them yourself without like sort of picking from a list of 4. So let's name this together. So first off, we see that our parent chain is obviously going to be this big cyclohexane right here. So our parent chain is cyclohexane. And so now let's see our substituents. So we have one hydroxy substituent here, one here, this one here, and then this one here. So I'm going to name those real quick. So here's our ethyl substituent. Here's a methyl substituent. And since we have 2 hydroxy substituents, this is going to be a diol. Okay? So now all we have to do is number it, giving everything the lowest number possible, especially the alcohols. So I'm going to start from this alcohol. Let me change colors. So we're going to be 1, 2, 3, 4, 5, 6, because we want to give specifically the alcohols a lower number, but also we want to give everything the lowest number possible. So we're going to have 3 ethyl, 4 methyl, and in this case you have to put the 1, 2 diol, even though this is a cyclohexane, because we have more than one alcohol. So methyl cyclohexane 1, 2 diol. But we're not quite done yet because we also have stereogenic centers that I've given geometry here and here. I gave you guys kind of a break because while both of these are technically stereocenters, I did not actually give them stereochemistry because I didn't want to overload you guys with this one question because it's a long one. So let's look at this first one here. So if we give OH, actually I'm going to erase some of these colors to make sure that everything is good. So with the diols, I don't think you drop the E because it would be putting N and D right next to each other. Like if we didn't have, sorry, I'm just trying to think of how to say this. If we didn't have that E, then it would look like this. Which I don't know about you, but if that were a word, I think I would cry. So that's why we put the E here instead of just dropping it off like just a regular OL. Okay, so I'm just gonna erase some stuff here. So again, it's important to note that if he were to ask for the stereogenic chemistry, like if he gave these 2 stereogenic centers stereochemistry, then you would also have to name those. But I didn't, just because I did not want to give you too much in this name, because I've already given you quite a lot. So let's just do this stereocenter first on 1. So OH is going to be 1. This group here is going to be 2. This one's going to be 3. So we see that, oh, it looks like R, but then we see that our lowest priority is not on a dashed wedge. So what we're going to do is, again, this is the way that I do it. You can do the swapping of the stereogenic centers, but I like to draw out the tetrahedral, label the different priorities. So like this dash wedge is 1, this solid wedge is 4, this one is going to be 3, and this one's going to be 2. I like to do this just because it sort of gets rid of any exceptions. So like there's no question about whether this is going to be S or if this is going to be R. And I pick it up, I twirl it around. So 4 becomes 1, 1 becomes 3, 3 becomes 4. So 1 is here, 3 is here, 4 is here. And then we see that this is indeed become S. So our first stereogenic center is going to be 1S. Okay? So now we're going to look at our second stereogenic center, which is we don't have to swap anything because we can see here that it already is the lowest priority is already on a dashed wedge right here. So OH is 1, this group is 2, this group is 3. We do the stereochemistry, we see that it's going to be 1S, 2S, and so then we're just going to put that in front of the name. So it's going to be 1S, 2s, 3-ethyl 4-methyl cyclohexane 1,2-diol. Yes, that is an ugly name. It's a long name. It's a hard name. I don't know if he would have you do this on a test, but I wanted to sort of touch on literally everything so that you would be able to see what you understand, what you don't understand, and what you need to go over. So does that make sense to everyone? Would we not put trans? So you can put trans, but since I put the stereogenic center, the stereochemistry conformations here, you don't need to put trans. So like technically, you didn't need to put 1s, 2s here. You could put trans, but the both of them would be correct. But I put 1s, 2s here specifically because you see these two stereogenic centers here. I did not give them stereochemistry, but if they had stereochemistry, then we would have two additional like S or R conformations here. So we couldn't say trans or cis. What? I would have talked to him about that if 1s and 2s was wrong. Because I personally believe that 1s, 2s, 1r, using the stereogenic conformations is more correct, in my opinion, than doing the trans or cis. He probably wouldn't accept it now, but if you do end up getting it wrong because you put 1s, 2s versus trans or cis, I would go to his office hours and talk to him about it, because again, this is his first time doing things online, and so he might just be not putting in all of the possible answers just because he isn't used to the online format, if that makes sense. Okay, so he did regrade some questions. Okay, good. That makes sense. Okay. Okay, so let's continue on with what product is formed in this reaction. So we can see here that we have NaOH, which means I'm going to rewrite this as Na plus OH minus. Let me fix that. So Na plus OH minus. And then we see here that we have an alkyl, that we have a halogen, which is a good leaving group, right next to an OH group right here. So if we look back on the notes, we see that specifically NaOH, which is a strong base, is specifically used in order to deprotonate this guy right here and then do an intramolecular SN2 reaction. So this O is going to replace that Br, and then we're going to end up with an epoxide, okay? So when we have a hydroxy group right next to a leaving group, a Br, a halogen group, and we see that we're using a strong base here, we're most likely going to be forming an epoxide. So our answer right here, would be B. Okay? Does that make sense? Okay.
So my only question is, so the NaOH, it picked up the hydrogen from the OH, right?
Yes.
And so how will we know like that will always happen? Like,
so I'm gonna swap screens again. So I'm going to share the PowerPoint again. If I can find it right here. So we can see here, I'm gonna scroll up. We can see here that specifically when, let me scroll up again. Yes, NaOH would also be a strong nucleophile. Where was it? It's seeing that we have an OH next to a halogen. That's the big thing about it.
so when we see that, we should just know that an epoxide is gonna form.
Yeah, so like you see here that we have a we have an OH group, which is a strong base next to a so we have this OH group here acting as our strong base. Then we see a hydroxy group right next to a good leaving group. Okay? Does that make sense? Because what's more likely to happen is this OH is going to get deprotonated by this OH here rather than the Br getting replaced. Does that make sense?
Yes, thank you.
So it's like being able to see where, just being able to recognize different types of reagents, and understanding how they'll affect it. Okay. Okay, so I have to swap screens again. Sorry for all the screen swapping, but okay. So what type of reaction will this be? So we see that we have what kind of alcohols? Oops, I just paused my screen share. So this is a tertiary alcohol, and we're using an acid. Whenever we see a strong acid along with an alcohol, we know there's going to be dehydration. So we know we're going to be doing an elimination reaction. So we're not going to do SN1 or SN2. And then we have to look at what kind of alcohol is this. This is a tertiary alcohol, so we're going to undergo E1 instead of E2. Okay? E2 would be undergone if instead of having this alcohol, we had this primary alcohol right here. Okay? Does that make sense to everybody? Okay. All right. So what would the previous reaction be if the substrate was changed to this? Okay, I have to stop looking into the future to see what my problems are. Again, I'm very predictable with these questions. But yes, we can see here that it's not SN1, it's not SN2. We have a primary alcohol, so it's going to be E2. Okay? So it's basically the same question again, except we're changing up our reagents and our substrate. Okay? So select all the reagents that can be used for dehydration. This is if you guys took microbiology with Ambivero, Dr. Ambivero, she had a lot of select all that apply questions, which were brutal, which inspired me to write this question. So this is like, okay, so select the different reagents that can be used to do dehydration. So we know we have to use a strong acid for dehydration. So H2SO4 or H3O can work. And then we also have to use and then we can also use a special reagent here, POCl3. Okay, so a lot of these questions are sort of like testing your knowledge of the different reactions that we talked about. So what I would recommend is I'll also post an answer sheet for this guy into the Google Docs with this. So what I would do is after you understand these reactions a little bit more, after you're more familiar with them, I would go back and try to do these questions again. Okay? Okay.
So why couldn't it be B?
B, okay, so I'm going to stop sharing and switch. I'm going to switch screens again because, let me see, SOCl. Okay, we see here that when we use SOCl2, instead of doing dehydration, we replace the OH with CO. I specifically chose POCl3 and SOCl2 because they're so similar, and I personally always got them confused. So if you got this question wrong, maybe you're less likely to get them confused, right? So does that make sense?
Yes,
Okay.
it does. So yeah, this one SOCl2 is like substitution,
Yes.
and all the other ones are like elimination.
SOCl2 is substitution. POCl3 is elimination. Those are the two that are really similar that a lot of people get mixed up, including me. Okay? Does that make sense?
Yes, thank you.
Okay, perfect. Let me swap again. Okay, so what would be the products of this reaction? So this is an acid catalyzed alpha cleavage of an ether. I know this because I see I have two equivalents of an HX along with an ether here. So what happens is I split the ether in half and I replace the oxygen with whatever that halogen is. So we're going to replace both sides of this with a Br, which then corresponds with this answer right here. Okay? Does that make sense? Because what occurs is we can also sort of understand this logically, because if we start with 2 HBr, then we cannot end up with an extra oxygen here. Because we start with 1 oxygen, but where did this second oxygen come from? So that's logically wrong. And then we can see here that, okay, we have 1 Br made up. We have 1, but where did the other HBr go? Why did we need 2 HBr or 2 HBr in order to just turn one of them into an alkyl halide? Same with this one. Okay? Does that all make sense? So like logically going through it, you could do that if you did not know the actual reaction by heart. So in this case, it would be D. Okay? So what would be the product of this reaction? So here's a thiol reaction. So remember when we use a thiol reaction, what happens is we deprotonate that SH into an S minus. And then what happens is it replaces it acts as a strong nucleophile in order to replace that Br there. And so then we end up with a disulfide, or a sulfide. Sorry, I was thinking about a disulfide bridge, but we end up with a sulfide, not a disulfide bridge. Okay, does that make sense? So we end up with C. Okay, this one is one of the harder ones, I think, because at least I personally did not focus on the sulfide reactions as much as the alcohol reactions, but they're just as important to know. Okay, does that make sense? Okay, perfect. Okay, so what is the product of this reaction? So notice here, we have an acid and a nucleophile. So what's going to happen here is we're going to do an acid catalyzed epoxide opening. Generally, when you have epoxides as your substrate, you're going to do some sort of opening. So if we had a strong nucleophile, such as CH3O negative, instead of the H2SO4 and the CH3OH, we would just do a nucleophilic epoxide opening. But in this case, we're doing an acid catalyzed epoxide opening. So we are going to attack the more substituted carbon, and we're going to add on this nucleophile in the opposite stereochemistry. So if we look through all of these, we have to see, oh, which one, first I like to look at, oh, which carbon was this CH3OH added to? In A, it was added to this carbon, so this one's wrong, because again, we are going to add to the more substituted carbon. This one, it added to the right carbon, so we're good so far. This one, it added to the wrong carbon. This one, it added to the right carbon. So now what we're going to do is we are going to compare the stereochemistries. Because remember, when we do an epoxide opening, we are going to replace the carbon-oxygen bond with inverse stereochemistry. So both of these inverse the stereochemistry. However, look at the OH. The OH stereochemistry should stay the same. So that means that B is wrong and D is our answer. Okay? Does that make sense? I know I probably went through that pretty fast, but I mean, it's getting kind of late. And I'm trying to get to chapter 10. Okay? All right. If there are no questions, I'll just move on. I think the next question is about if the product was changed. Yeah. So if instead of using the acid catalyzed epoxide opening, we used a nucleophilic epoxide opening. So what occurs here is that instead of adding to the more substituted carbon, this CH3O is going to add to the less substituted carbon. So now we just look for the opposite of what we did before. This one looks okay so far. This one is wrong. This one looks okay so far. This one is wrong. And so then again, we look to see if the nucleophile was added in the opposite stereochemistry, or if it was added in the opposite stereochemistry, then it's correct. This one was not added in the opposite stereochemistry. This one was. So our answer is C in this case. Okay? All these questions were really challenging. I did my best to make them as challenging as possible, so you won't be surprised by many other things that you come across. Are there any questions about these questions that I've made or the answers that I've given at all? If not, then I will go ahead and move on to chapter 10.
Yeah, just one final question for the last reaction. So
Okay.
when it's attached to less substituted, like how do you know which is the like looking at like that's why I'm just confused, because it has like the other stuff there.
Okay, let's zoom in real quick. Enhance. Um, so if we look here, let's look at the two carbons that are attached to the epoxide. This carbon here, this is a secondary carbon because it's attached to two other carbons.
Oh, I got it now.
This one's a tertiary carbon.
Yeah, okay. Makes sense. Sorry, thank you.
No problem. No, I'd rather you ask questions, because there are probably other people with that same exact question that either can't speak up because they're watching a video, or they don't want to speak up, which I understand. Yep. Okay?
Thank you.
No problem. All right, so then I think we'll go on to chapter 10. All right, everyone. I'm actually going to do an audible here. And since Dr. Dowdy hasn't gone over chapter 10 as or hasn't gone over the completely over chapter 10 as of this recording, I'm going to wait until Tuesday. What day is that? June 30th? Yeah, Tuesday, June 30th at 3 p.m. to finish up this review and go over chapter 10. And I'm going to try and also make some questions for you guys if I can, similarly to how I did chapters 8 and 9. And doing it on Tuesday, 1 will let you guys know more about chapter 10 as a whole, and 2, give me a little bit of time to make you guys some more questions, just so you guys have as many resources as possible. Okay, so I will do a test exam 3 review part 2 on Tuesday, and you should see that going up relatively soon in relation to this YouTube video. All right, thank you so much.